So in this lesson I'm going to look at contingency tables and combining events. And I'm going to look at an example and talk about the contingency table based on this particular example. And the example says a card is drawn from a standard deck. Event or is the red card is drawn. Event Q is that a queen is drawn. I want to draw a contingency table and evaluate the probability of or Q. So to draw a contingency table for some kind of event, what I'm going to do is draw, a little rectangular display of numbers here. And I'm going to put my events in along here. The first one I'm going to put in is this OR. Remember, that represents a red card is drawn. That's what that means. So we're talking about red cards. This whole column represents red cards. If a card is in this in this row, it should be a red card. The row below that should be the complement of that event. Now, what does that mean, the complement of the event? Well, the complement of any event is just the exact opposite. So, or complement, which we write with that little dash up there, means not a red card. A red card is not drawn. Or means a red card is drawn. Or complement means a red card is not drawn. Event Q is a queen is drawn. I'm going to put that up there. And right next to it I'm going to put Q complement, which means a queen is not drawn. It's just the opposite. In the final column I'm going to put my capital sigma. In my final row I'm going to put in my capital sigma. Remember, that just means my total. That's my total. This is my total in here. So if we think about our totals, this is the total, this is the red cards, the total number of red cards in a deck. Total number of red cards in a deck. How many red cards are in a deck? Well, a standard deck has 52 cards. Half of them are red, half of them are black. So half of all my 52 cards will be 26. So there are 26 red cards in a deck. There are also non-reds. In this case, non-reds in the pack of cards are black cards. So the non-reds, the black cards, there are 26 of those as well. Altogether giving me 52 cards. There's my totals. Along here, if I look at my bottom row here, well, this is the total number of queens in this. So this column represents all the queens. This one cell represents the total number of queens. How many queens in a standard deck? Well, there are 4 queens in a standard deck. And we know there's 52 cards in the standard deck, which means the number of non-queens. Remember, this is the total number of non-queens. This column represents all the cards that are not queens. There's 4 queens, so the remainder, 48 cards, will be non-queens. So that's my contingency table. I'm starting to fill it in. Now I want to look at, the different cells. So what does this cell represent? This cell in here. What does this cell represent? Well, for a card to be in this cell, it has to be a red card, and it has to be a queen. So any card that's a red card and a queen. Now there are only 4 queens. Half of those are red, half of those are black. So we've got 2 red queens and 2 queens that are not red. In that case, that would mean 2 black queens. Over here, again, the total number of things in this row is 26. So this cell in here has to be 24 because 2 plus 24 is 26. And what does that mean? Well, we're talking about red cards that are not queens. All the red cards that are not queens. There are 24 red cards that are not queens because there are 2 red cards that are queens. And again, in here, this has to be 24 as well because 2 plus 24 is 26. That means there are 24 cards that are not red and not queens. So I want to evaluate the probability of or Q when a single card is drawn from a deck. A single card is drawn from a deck. I want to find the probability of or Q. And we define probability as the number of ways an event may occur divided by the total number of possible outcomes. The total number of possible outcomes when I draw a card from a standard deck is 52. How many ways, the total number of ways the event may occur? Well, one thing I can do is I can count all the cards that are kind of red or queen. So if I count along this row, well, there's 26 cards that are red. I'm counting down here along this column, there are 4 cards that are queens. So if I count all those, that's 26 red cards plus 4 queens. However, you will notice that what I've done while counting is I've actually counted these two twice. I counted those when I was counting across, 2 plus 24, and I counted those when I was counting down, 2 plus 2. So I've got to remove one of those from the double count. I've counted this cell twice, so I'm just going to remove 2 there. 26 and 4, 30, subtract 2, that's 28. 28 over 52. Okay, and that will reduce. The 4 is a common factor, top and bottom. It's going to be 7/13. So when I select a card from a standard deck, a single card, the probability that that card is either a red card or a queen is 7 and 13. Let me look at another example. So this is a contingency table. It's a rectangular display of numbers. Used all the time in sciences, engineering, business world, very common thing. Let's look at another question here. In a group of 50 students, 20 took French but not science, 12 took science but not French, 4 took neither. Draw a contingency table and evaluate the probability that a randomly chosen student from this group studies maths or science. Okay, so again, the setup is pretty much always the same. I'm just drawing a few vertical lines and a few horizontal lines. My events here is a student takes French, and the complement would be a student does not take French. Up here, a student takes science. The complement would be a student does not take science. At the end of this row, we have our total. At the end of this column, we have our total. There's 50 students in the group, so the total number of students in the whole group is 50. 20 took French but not science. So these 20 have to be in the row that counts all the French, but they have to be in the column that don't take science, which is this column. So we're talking about this row and this column. Those 20 students in there, they do take French, but they don't take science. 12 took science but not French, so 12 students have to be in the science column, but in the non-French row. So the science column, not French, so there's my 12 in there. Okay? And 4 took neither. That means they didn't take French and they didn't take science. So where do they go? And that's an important cell to know in there. That's that cell in there. Think about why that is. Everyone in this row does not take French. Everyone in this column does not take science. So 4 took neither. Those 4 are going to go in there. And once I have that value figured out, I can fill in everything else into the contingency table. 12 and 4 giving me 16 students do not take French. This number here this value in here has to add to 16 to give me 50. I can work out pretty easily that that has to be 34. 34 plus 16 is 50. This value in here has to be 14, because 14 plus 20 giving me 34. 14 plus 12 giving me 26. 20 plus 4 giving me 24. This is my contingency table for this data. I want to find the probability that a randomly chosen student from this group studies Maths or science? No, that's a typo. That should be French or science. So, French or the science. Again, you'll often see that written as P of F union S. So what do? Well, I count all the students who took French I count all the students who took French, which will be along this row here. There's 34 students. I count all the students who took science along this column, 26. Notice I've counted those 14 twice. The probability of any event is the number of ways that event may occur divided by the number of total outcomes. A randomly chosen student taken from this group, the number of total outcomes is 50. Number of total possible outcomes, there's 50 possible ways I can choose a student from this group. The probability they studied French or science, count all the students who studied French, 34. Count all the students who studied science, 26. But don't forget to remove the double count. I've counted those 14 twice in there. Whoop. Subtract 14. So 34 plus 26, that's 60. Subtract 14, that's 46. So 46 out of 50, that will reduce to 23 out of 25. So if I choose a student at random from this group of 50 students, it's a 23 in 25 chance that that student studies French or science. Okay? So a 92% chance. Okay, let me look at another example. Here we're given probabilities, but we treat probabilities in exactly the same way, because to establish probabilities we just count. A and B are two events with the following characteristics. The probability of A is 0.6, the probability of B is 0.4, the probability of A union B is 0.8. I want to find the probability of A intersection B. So there's A, this will be A complement, this is B, this is B complement, this is the sum total, this is the sum total, sigma is my letter that's going in there. The probability of A is 0.6, that means A, the end of the A column, 0.6. Now A is divided up into two other kind of groups within here. The probability of B is 0.4. Remember, the sum of all the probabilities in any experiment is 1. And the probability of A union B is 0.8. Now remember, adding up A union B, I add up all this stuff, I add up all this stuff, I remove the double count. However, that means the only cell that I don't count here is this cell in here. So this is kind of the complement of A union B. So this cell in here is a really important cell. This is the complement of A union B. And if A union B is 0.8 and all the probabilities have to add up to 1, well, the complement of A union B has to be 1 subtract 0.8. That's 0.2. And from there I can fill in everything. This cell has to be the number I add to 0.6 to get 1, 0.4. This is the cell I have to add to 0.4 to get 1, that's 0.6. This has to be 0.4, since 0.4 plus 0.2 is 0.6. This has to be 0.2, because 0.2 plus 0.2 is 0.4. And finally, this has to be 0.2 also. And notice, you add everything up, it all should work out nicely. I'm trying to find the probability of A intersection B. Probability of A intersection B. Well, that's the probability of A and B. That's that. It's 0.2. It's 0.2. So these are contingency tables. Really, really, really useful things. Finally, I just want to look at deriving the addition rule here. I want to find the probability of A or B. And notice that's often written as the probability of A union the probability of B. What do? Well, I add up all the things along here, along the row called A. In this case, W plus X, that'll be W plus X in there. I add up all the things along this column. Whoop. Try that again. I hit the wrong thing. So add up all the things along this column. That's going to be W plus Y. Okay. This cell will be X plus Z. This cell will be Y plus Z. This cell would be W plus X plus Y plus Z. So what do? Well, I add up all the things along row A, W plus X. I add up all the things along column B, W plus Y. But then I've got to remove that double count. Notice I've counted W twice in there. And then we divide by the total number of things, W plus X plus Y plus Z. Okay, so more simply put, I suppose, to find the probability of A union B, we take the probability of A and we add it to the probability of B. But when we do that, there's going to be a double count here, so we've got to subtract the probability of A intersection B, and this is known as my addition rule for probability, and you're expected to know it by heart. Okay? However, if you know contingency tables and how they work, this just makes absolute sense. Okay? The complement of A union B will be that. Okay? It's whatever is in that cell. Okay, so practice contingency tables. We're in section 5.5.